Okay, before I keep going with new stuff, does anyone have any homework questions you want me to go over? Okay, so last time I talked about the 4 different force types that we're going to have and how to represent those in a free body diagram. And so today we're just going to work on taking that free body diagram and putting it into Newton's second law, which is, how we're always going to use these free body diagrams. So let me start by giving just kind of a review of what we did last time. So let's say we want to draw free body diagrams of both of these two. And let's say we have sort of a shallow incline on this side and a steeper incline on this side. And a pulley at the middle and a block over here of 5 kilograms. And a rolling cart on this side of 1 kilogram. And these are connected to each other by a cable that goes over this pulley. Okay, so remember that there are 4 force types. And so you always, with every force, you have to identify which of these types in order to draw it right on the free body diagram. The first one is kind of its own category. That's the weight. And then the second category is contact forces. And there are 3 of these that you need to be ready for. Pushing contact, pulling, and friction. And speaking of that stuff, I didn't quite give enough information to do this problem yet. So let's say that the motion of these bodies at this instant is this way and this way. Okay, so that's the direction of motion. And the coefficient of friction between the 5 kilogram block and the incline, let's call that 0.2. Okay, so I'm going to start with the 5 kilogram. I'm just starting at the left and working my way to the right. So draw a closed outline of the body in the orientation that it's shown. And then the first step is draw a downward force to represent the weight. Since the mass is 5 kilograms, this force is 5 times 9.81, so this is 49.05 newtons. I always leave the units off in the free body diagrams because I know what units I'm using. And now that we've drawn the weight force, now we have to go around the boundary looking for contact with the surroundings. The first place that I see contact is with the cable. So the rule for a pulling force from a cable is it's away from the body, parallel to the cable. So there's a line parallel to the cable. The force is away from the body. We don't know what the magnitude is, so I'm just going to call that T for tension. And then the second place I see contact is with the incline. there's friction with this contact. And remember that friction always occurs in a pair with a pushing force, okay, with a normal force. So I'm going to start with the pushing force. The rule for that is it's toward the body, perpendicular to the surface. So there's my normal force N. By the way, normal, the reason I use that N is normal means perpendicular. So that's a force that's perpendicular to the surface is what that means. And then there's also a friction force. The friction force is always opposite the velocity vector or opposite the direction of motion. So that is like this. And the magnitude of that force is the coefficient times the normal force. And remember that that is a number times this variable value n. That's not saying newtons. When I do newtons, I'm not going to put the, what they call those serifs on top and bottom of the n. I'm just going to do like a plain capital N. So you can always tell in my notes which one I'm talking about. So remember what this one is saying is the bigger the force is pushing these together, the bigger that friction force is going to be. Now you can go all the way around the boundary, and we've dealt with every place there's contact with the surroundings, so you know you're done with that. And now I'll go to the free body diagram of the 1 kilogram. There's a weight force straight down that's equal to 1 times 9.81, so 9.81 newtons. At the wheels, there's a pushing force from the ground that's toward the body, perpendicular to the surface. And this is not the same as this, so I have to give that a different name. But you can give it a different name by just giving them different subscripts. So like I could call this N1. I could call this one N5, and then this has to be N5. Just as, you know, I didn't have to put those 5s there because that 1 makes this a different variable than this, but those have to be different. And then the only other place where there's contact with the surroundings is at the cable. So that force is parallel to the cable, away from the body. And it's the same cable as this one, so I use the same variable. Any questions about those? That's pretty much what we spent the time on last class, is coming up with those free body diagrams. And now the next step is getting used to putting the information from free body diagrams into Newton's second law to actually do calculations. Okay, so here are the steps that I'm going to always follow for using Newton's second law. The first step is always to draw a free body diagram. If you don't draw free body diagrams when you use Newton's second law, you're going to lose points because that's an important thing to do. And the point of the free body diagram is to show you all of the forces that go into that go onto the left side of Newton's second law. So we just have to represent all, in this case, 1, 2, 3, 4 force vectors on the left side of Newton's second law, and we know then we've dealt with everything. The second step is to determine the axis that the thing can move along. So if the body can move along the x-axis, then the acceleration vector just has a variable in the A component and 0 for the Y. If it can move along the y-axis, you'd represent this acceleration vector as 0a. And one important thing about these is even if you can tell from looking at it that the thing is going to accelerate in, say, the negative x or the negative y direction, you don't have to put that sign in here. That'll come out in the math. So all you have to do is identify, is it moving along x or moving along y? Okay. And then the last thing is, if the thing isn't moving at all, then this can be 0. In fact, it can be moving as long as the velocity isn't changing because of the meaning of acceleration. So this is also true if you know that the velocity is constant. But most of the time when you do this, it's going to be because the object is at rest. Okay. And then the last step is put all this information into Newton's second law and use it to solve for variable values. And remember, what Newton's second law says is that you add up all the forces on the body, that's F net, all those force vectors, and set that equal to the object's mass times its acceleration vector. Okay, so now I'm just going to do a bunch of examples. Yeah?
Do we need to know the formal definition for the test of Newton's second law? Or no?
To remember this formula?
No, like in words.
Oh, that's more of like a thing. I guess no, you don't have to. On quizzes, I do sometimes ask to tell me what Newton's second law is, and even just F equals ma would be fine. But and on exams, that's given as one of the equations, so you don't have to remember it on exams. Any other questions right now? Okay, so yeah, let's just get into a bunch of examples. So first, let's say we have a mass of 20 kilograms that's connected to the ceiling by a cable, and let's say we're applying an additional force of 5 newtons down. And we want to calculate the force vector applied to the mass by the cable. The first step in doing this is to draw a free body diagram. So there's a weight force down that's equal to 20 times 9.81. That's 196.2 newtons. And then we're given that there's an additional force down of 5 newtons. And then if you keep going around the boundary, the only contact point is with the cable. So the rule for a pulling force from a cable is that force is away from the body, parallel to the cable. And I'll give it the variable name T for tension. The second step is to think about the acceleration. This is just hanging in place. So there's no acceleration here. So that's just going to be zeros. And now we can put these two bits of information into Newton's second law. All right, and for each one of these, what we're doing is, when you get used to this, you won't have to draw the coordinate systems. But for each one of these forces, we're doing what we did in the vector assignment. We're putting the tail of the vector at the origin and figuring out the coordinates of the head of the vector. So for the weight force, it's a vector like this with a magnitude of 196.2. For the 5 Newton force, it's a vector like this with a magnitude of 5. And for the cable force, it's a vector like this with a magnitude of t. We don't know what t is. So one by one, we're going to go through these forces and write down the coordinates of the heads. So for the weight force, what are the coordinates of the head of that vector? Yep, 0, negative 196.2. Okay, and then for the 5 Newton, what are the coordinates of that head? Yep, 0, negative 5. And what about this one? Well, we don't know a number for it, but we know the magnitude is t. What are the coordinates of the head of that vector? Yeah, 0, positive t. That's all the forces. And so now we know that this is equal to the mass times the acceleration vector, which we figured out was 0, 0. And so that gives us 2 equations. This is a vector equation, so it always gives us 2 separate equations, one for the x components and one for the y components. The x components say 0 plus 0 plus 0 equals 20 times 0. So that equation reduces to just saying 0 equals 0. We can't use that to solve for anything. So we can just forget about that one in this case. But the second one is useful here. It says negative 196.2 minus 5 plus t is equal to 20 times 0. So 201.2 negative plus t is equal to 0. So solve that and you get that t is equal to 201.2 newtons. Okay, that's almost the answer to this question, but the way I worded this problem was, what's the force vector that the cable applies to the body? So how do we go from this value of t to the vector that that cable applies to the body? Well, notice that in Newton's second law on the left side, we've already given representations of all of these force vectors. We just didn't know yet what that variable t was. So now this is the vector that we're looking for, and all we have to do is plug t into it. Okay, so the force by the cable is equal to 0, 201.2. Or another perfectly fine way to express this is that's in the positive y direction. So draw an arrow in the positive y direction, and it has a magnitude of 201.2 newtons. Okay, so if you had a cable that you knew was going to break if the tension in it exceeded 200 newtons, then this calculation has shown us that that would break. Okay, and that's like a really useful engineering application of this stuff, is figuring out, and it gets obviously much more complicated than that as you go on in engineering classes, but a lot of what you're doing is just trying to figure out how strong these different materials have to be so they don't break in your the application that you have, Anyone have any questions about that? Okay. So now let's do one where an object is moving. So let's say this cart is moving along a horizontal surface. And let's say we have a 20 Newton force this way, a 10 Newton force this way, a 30 Newton force down, and the mass is 10 kilograms. And we want to figure out two things. What's the acceleration vector? Of the cart? And second, what's the force vector on the cart by the ground? And then actually, let's ask a third question. Can we tell whether this is speeding up or slowing down? Okay, so the first step is always to draw a free body diagram. There's a weight force down of 10 times 9.81, so that's 98.1 newtons. They're the three forces that are given, so a 10 that way, a 20 that way, and a 30 down. And then the last contact with the surroundings is at the wheels. That's a pushing contact from the ground, so that's perpendicular to the surface toward the body. The next step is what can we say about the acceleration? So is this free to move along the x-axis or the y-axis? X, yep. And so we're just going to treat this acceleration for now as a0. And it's going to give us the value of that a. And, you can look at this and it's not too hard to say it's being pushed harder in the negative x direction than in the positive x direction. So the acceleration is going to come out negative. But like I said before, you don't have to write that down yourself. That'll just come out in the math. Okay. And now we'll go to Newton's second law. So what are the components of the weight force? Yep, 0, negative 98.1. What are the components of the normal force? That's in the positive y direction. So that's just going to be 0 positive n. The 20 is in the negative x direction. So that's going to be negative 20, 0. What? I'm doing the 20 here first, and the next one is 30, yeah. So the 20 is in the negative x direction. The 30 is in the negative y direction. So that one is going to be 0 for x, negative 30 for y. And then last, the 10 is in the positive x direction, so that's just positive 10, 0. And now we set these equal to the mass of 10 times the acceleration we just determined. And we have two equations again. The x equation says 0 plus 0 minus 20 plus 0 plus 10 is equal to 10a. Or in other words, if you add this all up, that says negative 10 is equal to 10a. And so if you solve for a, you get negative 1 meter per second squared. Any questions about that? And then from the y equation, we got negative 98.1 plus n plus 0 minus 30 plus 0 is equal to 10 times 0. So that says negative 128.1 plus n is equal to 0. And so n is equal to positive 128.1 newtons. Again, though, that's not the format that I asked for the answer to be in. I asked for an acceleration vector and a force vector that the ground applies to the cart. Okay, so for part A, how are we going to come up with the acceleration vector? Well, remember, with all of these, anytime it asks you for a force vector or an acceleration vector, you've already determined what those vectors are. You just didn't know all the variable values yet. So this is the acceleration vector once we plug in the value for A. Okay, so for part A, the acceleration vector is negative 1, 0. Or in other words, it's in the negative x direction with a magnitude of 1 meter per second squared. So just like our intuition kind of told us, this thing is going to be accelerating to the left because that's where the bigger force is pushing. And then for the second one, now we want the force vector applied to the cart by the ground. That is this vector. We just didn't know what the n was yet, and now we do. So now we can say the force from the ground is equal to 0, 128.1. Or another way to write that is it's in the positive y direction with a magnitude of 128.1. Any questions about either of those? Yeah.
Are we expected to write out all the zeros from the?
No. I'm just doing that to make it clear what I'm doing. I'm going to stop doing that right now too, actually. Any other questions? Okay, so there was a part C, and that was, can we tell whether this is speeding up or slowing down? So this is accelerating to the left. Is that enough for us to know whether it's speeding up to the left or? It's not. What's the extra information we would need in order to know whether it was speeding up or slowing down?
Direction of motion.
Yeah, perfect. We'd have to know the direction of motion, or the direction of the velocity vector. Then if we knew before this problem started, if we were told that at this instant it's moving to the left, then we could say acceleration and velocity are in the same direction, it's speeding up. Or if we're told that at this instant it's moving to the right, then velocity and acceleration are in opposite directions, and it has to be slowing down. Okay, but the thing is, with problems like this, you're normally not given what direction it's moving at that instant because it doesn't matter for the calculation. No matter which way it's moving at that instant, all these calculated values are going to be the same. Okay? But there's one kind of problem like this where you are given the direction of motion. That's any time that there's friction in the problem. To do problems like that, you have to know which way it's sliding. And so with friction problems, I'm often going to ask, is it speeding up or slowing down? Because we have to have all that information anyways. Okay? So not enough information. Okay, let's do one now with friction. Let's say this has a mass of 3 kilograms, and there's a force pushing this way of 20 newtons, and a force pushing down of 10 newtons. And at this instant, let's say that the object is moving to the left. And we'll say that the coefficient of friction is 0.3. And we want to know what's the acceleration vector. What's the total force vector from the ground that's applied by the ground? And then third, we want to know whether it's speeding up or slowing down. Okay, so the first step is to draw a free body diagram. There's a weight force down of 3 times 9.81, so that's 29.43. There are these two forces, a 20 here, a 10 here. And then there's the contact with the ground that's made up of two parts. There is a pushing contact from the floor, call that N. And then there's a friction force that's opposite the direction of motion. So it's this way, and that's equal to 0.3 times that normal force N. And the reason you have to know the direction of motion is so that you know the direction of the friction force. Any questions about the free body diagram? So now we have to figure out the direction of motion. Is this free to move along X or Y? X, so I'm going to write this as A0. And now Newton's second law. The 20 is in the positive X, so that as a force vector is 20, 0. The 10 is in the negative Y, so 0, negative 10. The weight is in the negative Y, so that's 0, negative 29.43. The normal force is in the positive Y, so 0N. And the friction force is in the positive X, so that's 0.3N0. And then you can count up to make sure that you got them all. We have 1, 2, 3, 4, 5 in the free body diagram, 5 in Newton's second law, so that's it. And then these are equal to the mass of the body, 3 kilograms, times what we figured out for the acceleration vector, A0. And now I'll break it up into X and Y parts. The X equation says 20 plus 0.3N is equal to 3A. On the last problem we did, we were able to solve for A from this. In this case, we can't because that N appears in this equation. So we have one single equation with 2 unknowns. So for these friction problems, what you're always going to have to do is use the Y equation to solve for N, and then plug that N value into the X equation. So now I'll go to the Y equation. It says negative 10 minus 29.43 plus N is equal to 0. So that says negative 39.43 plus N is equal to 0. And solve for N, and you get 39.43 newtons. And now that I've solved the Y equation, now I'm going to plug that into the X equation. And so that says now 20 plus 0.3 times N, which we now know, is equal to 3A. And so this all comes out to be 31.83 is equal to 3A. And so A is equal to positive 10.61 meters per second squared. Okay, now that we have all those variables, now we can go back and answer the questions in the form they were given. Part A, we wanted to figure out the acceleration vector. So we'll just plug this value now into this acceleration vector. So the acceleration vector is equal to positive 10.610 or in other words, that's in the positive x direction with a magnitude of 10.61. For part B, there's one thing you have to be a little careful of in questions like this about friction. What's the force that the ground applies to this block? Well, it's actually broken up in all of these problems into two parts. There's the pushing force and then the friction force. So we want to account for both of those in our answer. You know, all of this circled stuff is the force on the block by the ground. So plug N in for both of those, and you get, so the force from the ground is, so that was 11.43. Hold on a sec. Let me write it in two steps. So this is 0.3 times the normal force, which was 39.43, plus the normal force, and so you get a force vector of 11.83. 39.43. So the force from the ground, if you want to visualize that, in this case, it's a lot easier to just give your answer as vector components. But that's going to be, you know, go over 11.8, go up 39.4. So that total force vector would be at an angle like that. Any questions about that? Okay, and then what about speeding up and slowing down? Well, we figured out that the acceleration is in the positive x direction. The velocity was in the negative x direction. So the velocity and acceleration are opposite. So it's slowing down. Any questions about that? Okay. So let's do a couple now where I'll just give you some time to work through the steps. Just make sure all this stuff is making sense. So let's start out with a cart like this with a mass of 2 kilograms. And let's say we have a force of 6 newtons there and a force of 4 newtons there. Calculate the acceleration vector and calculate the force vector from the floor. The first step is drawing a free body diagram. So take a couple minutes and see if you can draw that free body diagram. Okay, so this should look like this. A weight force down of 19.62. A pushing force up of n, and then 4 this way, and 6 this way. Okay, so next, figure out how this can move and write your expression, your starting expression for the acceleration. So this one is free to move along the x direction, and so we're going to express the acceleration vector as a, 0. Next, write out Newton's second law. Okay, so Newton's second law says the 4 is in the positive x direction, so 4, 0. The 6 is in the negative x direction, so negative 6, 0. The weight is in the negative y direction, so 0, negative 19.62. N is in the positive y direction, so 0, n. And that's equal to the mass of the cart, 2, times what we came up with for the acceleration vector. And now that we have this equation, see if you can go through from Newton's second law and figure out the answers to these two things, the acceleration vector and the force vector applied by the floor. Okay, so the x equation says 4 minus 6 is equal to 2a. And so a is equal to negative 1 meter per second squared. The y equation says negative 19.62 plus n is equal to 0. So n is equal to 19.62 newtons. And now to put these into vectors, plug this one into our expression for the acceleration vector. It gives you negative 1, 0. And plug this one into that force vector, the 0n force vector, and it says that the force from the ground is equal to 0, 19.62, or an upward force of 19.62. Okay, so that's the idea of using Newton's second law. We are going to use this in 3 kind of specific configurations besides these single bodies. So I think we can get through one of these without too much problem today. So specific cases for Newton's second law. And there are 3 of these. The first one is collections of bodies in contact that have the same acceleration. So that's the one we're going to get to today. Then we're going to talk about rolling and sliding on inclines. So we've talked about rolling and sliding already when the surface is horizontal, but what about when the surface is at an angle? And then the third one is collections of bodies with different accelerations. And these are always going to be bodies that are connected by cables and using pulleys. So those are basically the next 3 lessons we're going to do. So today I'm going to start with collections of bodies that have the same acceleration. And an example of this would be say you have 2 carts that are in contact, and you have forces applied here and here. And we're usually going to want to calculate the accelerations that these things have. Notice that since they're in contact, whatever they do, everything's going to do it the same way. You know, you can't have one of those accelerating a lot and one accelerating a little. You could if they separated from each other, but the way those 2 forces are, it's going to be holding them together. Okay, so that's why those bodies have the same acceleration. And so, yeah, we're going to want to calculate the acceleration of both of those. And we're also going to want to usually calculate the contact force between them. So like the force that the bigger one applies to the smaller one, and the force that the smaller one applies to the bigger one. And so this is going to be our approach. First, we're going to isolate the whole system. That, in this case, that would mean both of those 2 carts together. We're going to treat it like our chosen body. And we're going to use this to calculate the acceleration. And then second, we're going to isolate an individual body and we're going to use the acceleration from step 1. Okay, so let me go through an example problem. So let's say we have a horizontal surface. And we have a 5 kilogram cart here in contact with a 10 kilogram cart here. And a 25 Newton force. And going the other way, a 50 Newton force. And let's say we want to calculate the force vector on the 5 kilogram by the 10 kilogram. Well, notice that in asking this question, I didn't say anything about calculating the acceleration vector. But if you tried to do it without calculating that acceleration vector, you couldn't do it. So even when it doesn't ask for that, we're going to follow this approach. First, isolate the two things together and calculate the acceleration. Okay, so free body diagram of the whole thing. We have a weight down of 15 times 9.81. So that's 147.15. And we have a 25 over here and a 50 over here. And then we have a pushing force from the ground. I'll call that N total, just so I don't make the mistake of thinking that that's, like later when I isolate one of these two things, to think that that's going to be the pushing force on one of those two. It's not, it's the combination. What about the acceleration? Is this free to move along X or Y? X. So that'll be A0. Newton's second law says 25(0) plus negative 50(0) plus 0, negative 147.15 plus 0 N total. And that's equal to the mass of the whole system, 15 kilograms, times our acceleration. Okay. And now I'll go to the X equation, and it says 25 minus 50 is equal to 15A. So negative 25 is equal to 15A. So A is equal to 1.6 repeating, this is negative, meters per second squared. And now you can plug this into the acceleration vector. And what we figured out is that the acceleration of each one of these bodies is negative 1.6 repeating 0. Or another way to say that is it's in the negative X direction. Okay, so we solved for something that we weren't even asked for, but we're going to need that to solve for the force on the 5 by the 10. Since we're asked for the force on the 5, we might as well isolate the 5, so because that's directly the forces that we're going to be able to calculate. So now I'm going to draw a free body diagram of the 5. Does the 25 act on the 5? Yes. Does the 50 act on the 5? No. That's important. Okay. So it's only the things, it's the weight, and then only the things in contact with the boundary that you're choosing. So we have the weight here. That's 49.05. We have the 25. Keep going around the boundary looking for contact, and there's a pushing force here from the ground. I'll call that N5. And then there's one more place where there's contact. Where the two things are touching each other, the 10 is pushing on the 5. So the rule is perpendicular to the surface, toward the chosen body, and I'll give that the name R. Okay. Well, normally the next step is to figure out what we know about the acceleration vector, but this time we we know the acceleration vector. We've already calculated it. It's negative 1.6 repeating 0. Okay, we got that from the first step. So now we can go to Newton's second law. And we get 25, 0 plus negative r, 0 plus 0, negative 49.05 plus 0, n5 is equal to the mass of our chosen body. That's 5 this time. And the acceleration is negative 1.6 repeating 0. So now, not part A, the x equation is what I meant to write here. Says 25 minus r is equal to 5 times, so that's what, 25 thirds, so that's negative 8.3 repeating. And so now solve for r, and r is equal to 16.6 repeating. Plug that into the force vector we want, and we get that the force on the 5 by the 10 is equal to negative 16.60. Or in other words, that's in the negative x direction. So that's this way at 16.6 repeating. Yes?
Wouldn't you be adding the 8.3 repeating to the other side, making it 30?
Correct.
3.3.
Thank you. Okay, so yeah. So let's go with 33.3. And then the signs are right on these, the directions. So it's kind of interesting looking at that number. I mean, you'd look at this problem and you'd say, well, like, how hard are these two things pushing on each other? If you had to guess, you'd probably say, well, it's either 25 or it's 75 or it's 50 maybe, you know. Those are the numbers that pop up. It turns out it's none of those. It's this complicated thing that has to do with the interactions of those forces and the way that thing is accelerating. Okay. And I want to point out one more thing. I'm not going to do a problem like this right now, but if these forces were pulling in the opposite directions and these were connected by cables, you could do this problem the exact same way. You just have to deal with the fact that it's pulling forces instead of pushing forces. But you'd use the exact same approach. You'd first isolate the whole system, calculate the acceleration, and then isolate one of the individual things. Okay? Let's stop there. That felt like a lot today, didn't it? I thought so too. We are, I will put it on D2L for sure, but I'm pretty sure that I can't be here on Monday. So that means there's no classes or labs all week next week. It's like mini summer vacation, except it's cold. Okay.